Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. Today we will continue our discussion about the new chapter, which is in chapter 6. It's supposed to be in chapter 6 here, which is eigenvalue problem. In this chapter, we will discuss about if we are given a matrix A, for example. A is a n by n matrix, so that we have A11, A12, A13, A21, A22, A23, A31, A32, A33, and then we want to find the eigenvalue for this matrix A. The first thing that we must know that this A must be a symmetric matrix, because we will later on discuss about a theorem, and then that theorem stated about the eigenvalue. And then after that, we also have two methods, which is the first one we call it power method, and the second one we call it shifted power method. And the first one is theorem. So now let's look at about this one as the introduction. The eigenvalue problem, let's say, as I said just now, given A is a n by n matrix, and we need to determine the scalar lambda and the non-zero vector V such that AV is equal to lambda V, where V is an eigenvector and lambda is an eigenvalue. So we want to find the value of this lambda. And then we have a theorem. Now let's say or suppose that A is an n by n symmetric matrix, then the eigenvalues of matrix A are all real numbers. So that meaning that we cannot have a complex number. And we can determine these real eigenvalues by using Gauge-Gorin theorem if we are given a matrix A. So for the Gauge-Gorin theorem, the purpose for this theorem is to roughly locate the position of our eigenvalues, where the first thing we need to find the radius of a circle that is defined by the formula of number 1 here. And also the second that we need to do is we need to look at the circle with radius Ri and the center at the Ai, and our center is defined by the formula of number 3. And let's say now we want to apply this theorem. So for example 1, use Gauge-Gorin theorem to identify the position. So we want to identify our position of our eigenvalues of the given matrix, so that we can apply this Gauge-Gorin theorem. The first one, we find what is our R1 radius, and then our center, and then because we have 3 column, so meaning that we have 3 column and also 3 row, so that we have R1, R2 and also R3, and same for the center. And then we can identify where is our eigenvalue is located. So this is about example 1. And then let's look at the second example. given the matrix A, and then A, is it possible that the eigenvalue of A is in complex form, and why? And B, use Geschgorin theorem to identify the interval where the eigenvalues of A are located. Of course, the first one here, it is not possible because matrix A is symmetric matrix, meaning that it is symmetry. Here we have the diagonal of the matrix is given by what I underline with the red one, so that we can see this matrix is reflected at the diagonal. So in other words, we also can say that this matrix A is symmetric matrix. So the answer for A, is it possible? So meaning that it's not possible. Since A is 3 by 3 matrix, 3 by 3 symmetric matrix. And by theorem, if A is n by n symmetric matrix, then all eigenvalues of A are real numbers. And then use Geschgorin theorem to identify the interval where the eigenvalues of A are located. So B, we need to use the eigenvalue, the Geschgorin theorem. And the Geschgorin theorem is given by Ri. Ri is equal to let's look at this one. Okay, I'm sorry. This one. Ri is equal to summation from j is equal to 1 and then by Geschgorin theorem, the first is Ri is equal to absolute value, the thing that is not the diagonal. So the first thing is is -1 at the row 1, and then also 3, so that we have absolute value for -1 plus 3, and then our radius for row 1 is 4, and we also will get radius 1. And for this row, our center is z minus 5 less than or is equal to 4. So from this one, we can have our center is 5 and our radius is 4. And then we go to the next row, R2, where we can find our radius, which is the thing or the summation for the element that is not diagonal. So that we have -1 plus 0, and then we have 1, while for the center is z minus 4 less than or equal to 1. So from here we know that our center is 4 and our radius is 1. And for the row 3, we have absolute 3 plus absolute 0 is equal to 3. And the center is z minus 4 less than or equal to 3. So from here we have our center is 4 from here, and the radius is 3. And then what we need to do, how can we identify where is our eigenvalue is located? So from 1 here, actually this is a circle with radius for center at 5. So that here, let's say we have 5. And then meaning that here is our 9. 6, 7, 8, 9 is the radius. So on the left, we have meaning that if we draw or sketch the circle, we will have a big circle with radius 4. For number 1. And then for number 2, we have center at 4. Here is our 4. And then the radius is 1. So that now the circle, it looks like this. This is our second circle. And then for the third row, we have radius 3 and our center also at 4. And then we have up to here, center at 4. Like this. And at the bottom we have like this. So that our eigenvalues must be in this circle, or what we can say that therefore lambda I or lambda 1, 2 or 3 must be in element of 1 to 9, because we have a range for this one from 1 to 9. It must be in the circle from the Gauge-Gorin theorem. So this is how we determine or we identify the values or the position of the eigenvalues of the given symmetric matrix. So now let's look at example 3. Show that all eigenvalues of A are positive. Again, we need to use Gauge-Gorin theorem. Using Gauge-Gorin theorem, now we need to determine what is our R1. So we can see the first thing is this one is symmetric already. A is symmetric. So that we can show all our eigenvalues are positive. And then for the R1, we must add all the element that is not diagonal. That we must add 2 and absolute -1. We get 3. While for the C1, we will have absolute z minus 4 less than 3. Then from this one, we can have the center is at 4, while the radius is 3. And then for the row 2, we have 2 and also 1 that are the element that is not diagonal, so that we can have absolute 2 plus absolute 1. Again, it's equal to 3. While for the center is z minus the element of diagonal must be less than or equal to the radius. So that we have our center is 6 and the radius is 3. And this last row, we have radius, which is absolute negative 1 plus absolute 1 is equal to 2, while the center is z minus the element of diagonal here, 12, less than our radius. So that our center is at 12 and the radius at, or our radius is 2 for this circle 3. And then next we need to sketch the graph, our circle, all the 3 circle. What we can have for the first one is center at 4. Let's say here is our 4. And the radius is 3. So that on the right we have up to 7. So our circle, the first circle is center at 4 with radius 3. So that we will have like this. And for the second one, I'm sorry, my drawing is bad. The second one, center at 6. So here is our center. And the radius is 3. So it must be up to here 3. And to the right, we must up to 9. So that we will have our second circle that is given like this. We can draw. So this is our second circle, while the next one is center at 12. So here is 10, 11 and 12. And we have our center at 12. And the radius is 2. So that to the right, we must have up to 14. While to the left, up to 10. And then we can have our third circle. We have like this, our third circle. So meaning that now our eigenvalues must be element from 1 to 9, 1 to 9, union of 10 to 14. And this is proof, or this is show that they are all positive. Okay, this is the two example about how can we determine the position of the eigenvalues if we are given a matrix, and we can identify these eigenvalues by using Gauss-Jordan theorem. Okay, that's all for now. Thank you very much.